Hey darts fans, that's Timo Newman here, the transporter. Welcome to the good ship Undarted Waters, and here we are at the end of this particular voyage, this perilous voyage, the physics of dart flight. This is part 5, and finally we can rip our oxygen masks off and let the air into the room, because today we're going to look at the effect of air resistance. Okay, so without any further ado, I'm going to get the old whiteboard. And I have to say, this video is so different to how I thought it would be. That's kind of why it's been a couple more days than I planned to make this video. So I mentioned Richard Feynman earlier on in this series, the famous, very famous Nobel laureate physicist from the United States, who was active between the 1940s and the 1980s. And I quoted him. He said, you know, if you can't explain a piece of science to a child, then you don't understand it. You know, even though he was a brilliant theoretician, he was wonderful at explaining science without having to resort to lots of equations and complicated jargon. But another thing that he would have been very strong on is to say that a physicist, a good physicist, should be able to approximate the magnitude of an effect and understand whether it's a strong effect or not. And I have failed Richard Feynman. I've gone to so much lengths to calculate the effects of air resistance. You know, I've got all these pages and pages of equations that I'm not going to bore you with. But last night I finally worked out how strong it is for a dart. I'm going to leave those in for a second, but here's like half of a dart. Here's the stem and the flight, okay? And to my astonishment, it was much, much smaller than I expected. And so for the last 24 hours, my brain has been at fever pitch trying to work out what is going on, and I think I understand it. And that's what I'm going to talk about today. So a little bit of a preamble there, but this is a totally different presentation to the one I thought I was going to give a day and a half ago. But let's get on with it and see how we go. So air resistance. I've drawn this picture a few times now. Here's a dart in mid-flight. Okay, it's a bit long for a point, isn't it? I can't even rub it out with my finger for some reason. There we go. Right, something like this. Right, and what I've been saying, and this is all perfectly true, is that the two forces acting on this essentially are the force due to gravity and the air resistance, which will essentially push back against the dart in its direction of travel. Okay, sorry about that banging there. Air resistance. And in the last two videos, we pretended that we were in a vacuum on Earth and we had gravity switched on, and we worked out, we talked about these what are called parabolic trajectories. And in the last video, I actually talked about how you can tune the angle of release of the dart to have the smoothest possible flight of that trajectory, where it has the minimal velocity, the minimal effort. And I believe that that must be the optimal way to throw a dart. And I'm going to talk about that a lot more in a new series where we're going to look at that for different elite players. So I'm going to take the vital measurements of elbow position and forearm length and all that good stuff for various elite players and work out what their Goldilocks angles are for various targets on the board. Excuse me. So that will be coming up very shortly. But in terms of just this basic science series on the physics of dart flight, this is the final video, because we just have to talk about this other force, air resistance. Now, I'm a biophysicist. I'm not an aero, what do they call it? An aerodynamics engineer. Is that what they call? Engineers and scientists that work on, you know, planes and such. They call, what's that called? Aeronautical engineering. That's not my background. So I've had to learn quite a lot of engineering terms in order to get my hands on this problem. And so let me just maybe zoom in here on the flight, okay? So that flight of the dart there, let's just look at one of the flights of the dart coming out of the back of the dart there, okay? Something like that. And imagine the dart's traveling in this direction. So essentially there are two different kinds of force that the air can enact on that dart flight. And the one that I thought was the most important turns out to be the least important. So my intuition was way off. It was only when I calculated it I found out how small it was. So one effect is called skin friction, and that is the air resistance between the surface of the dart and the air, okay? The air passing by. So if you imagine you've got something flat like this tea coaster here, and if that's moving through the air in this direction, that kind of sliding of the air across the face is called skin friction, and it will be a frictional force on the movement of this, okay? So that depends on the area here, all right, and it will be pulling it back in this direction. It's literally like a friction effect, but it turns out that that is absolutely tiny. So when you have a dart flying through the air, it basically doesn't really feel any of this so-called skin friction from the air, okay? Now, the other kind of air resistance is called form drag, and that comes if I were to have this thing moving through the air, but if I tilt it at an angle but move it, so let me do it towards you. So this is with just the skin friction, but if I tilt it, it's got the skin friction, but it's also now got a force that's actually pushing it in this direction, okay? And I never considered that because I always thought about darts that were moving in a perfectly straight line to their target, okay? I mean, it's going through that parabolic arc, but the orientation of the dart is always along its trajectory. So you wouldn't have this thing called form drag, but if you do have a slightly different angle, you get this other kind of friction called form drag, which will also retard the object. So I realized, okay, that there is a little bit of that other thing. I'm going to have to pull one of these darts out of the board here. I'm going to pull this one out, okay? Here's a dart with a regular flight on it. So when that dart's going through its parabolic trajectory, okay, even though if it was perfectly straight, meaning that if I aim it towards you, it's perfectly following, you see how essentially the back is always catching up with the middle. So the center of mass of this dart is somewhere here, and that's really the thing that's kind of moving through that trajectory, and the back's always sort of catching up. And what that means is that it does have a little bit of form drag, which pushes on the bottom here, and this is really what tilts the dart, okay? I had a question from a pal of mine, Trevor, who asked about this, and it's this form drag that tilts the dart. I thought that was a small effect. It turns out to be the biggest effect. So there you go. So that form drag, which is what actually tilts the orientation of the dart, even if it's perfectly aligned, it's going to push it in this direction from the back. That turns out to be about 3 times bigger than the so-called skin friction. But it's still really small. And when I put all of these numbers that I'd worked out into my computer program that calculates the trajectory of darts, with all of this stuff I've worked out for air resistance, the difference in where the darts will land, even with the form drag, turn out to be 1 to 2 millimeters. Tiny, tiny. So in other words, the dart, if that's the dartboard there, and this is the trajectory. Now let me do a better pen if you can see. if this is the trajectory in a vacuum, then the trajectory with the air resistance here, the dart will just come in literally a few, 1 to 2 or 3 millimeters lower. Absolutely minute effect. Okay. And I couldn't believe it. I thought, well, this can't be true. This can't be true, because people spend a lot of time thinking about their flights and all this kind of stuff. So I did an experiment. So I'm going to pull these other 2 darts out of the board now. I decided to change the surface area of the flights drastically on 3 darts and just test, do they really land in the same place if I throw as consistently as I can? So I've got one regular flight. I've got a flight where I've taken about probably a third to a half of the flight off, and then the third one I've taken even more off. So there's only maybe about, yeah, you can see that that one's even smaller. This has about a third of the flight left. This maybe has 2/3 of the flight, and this has the whole flight. And as you saw there, I just threw them all into the bull area there. You can just play with these darts. You know, it doesn't make any difference. So the experiment with these 3 darts is consistent with my calculations, that even that form drag is, you're talking about millimeters where the dart ends up on the board. But I'll tell you what though, and this is I think the key to the flights, this dart with the smallest flight here is a little bit, you need to be a little bit more careful when you throw it. Okay, because I tried even more. I took actually nearly everything off, and here's a flight with nearly everything taken off. Okay, and I can still throw a dart with this, but the dart is not very stable. Okay, so what I've now realized is that pretty much the only thing that the flight really does for the dart is even out any error when you first throw it. So if you happen to throw a dart, if it's coming towards you but I release it at an angle, there's going to be a lot of form drag. Okay, so there's a tiny amount of form drag even if it's very straight, and that's just because the dart's going to go through a parabolic arc and get pushed at the back. But there's much bigger form drag if you release it at, even though it's coming towards you, if I release it very poorly and it's coming at an angle, the form drag will push this flight and the dart will probably wiggle a bit and straighten up. Now that form drag is much bigger. That's actually like 10 times bigger, and you're not talking millimeters anymore. Now you're talking centimeters. Okay, so if you release the dart poorly, this trajectory is going to come in centimeters low. Okay, which is kind of what my intuition was, that the drag must make an effect, but it only makes an effect, I believe, based on my calculations and based on this experiment, only makes an effect with a poorly delivered dart or a poorly released dart, where the back's going to wobble and settle down during that fraction of a second of flight. Okay, so I think this is kind of a big deal. I'm someone that hasn't experimented with my darts. These are the same kind of darts that I started with, nearly 2 years ago now. I've just not experimented except for doing butchery like this on the flights. I know some people are really into that, and I'm sure they can really add a lot to this discussion. But all I can say is, based on the physics that I've done and I can remember the word now, aeronautical engineering, based on those concepts, a very well released dart that's very straight will have a very small amount of drag on it. And these flights, which are drastically different, so there should be a factor of 3 difference in the amount of drag that these darts experience, but it barely makes any difference to where they land on the board. You're talking millimeters if I try to throw very consistently. Okay, so that's really, I think, all I want to say about air resistance, is that it's a bit of a damn squib, in other words, except perhaps the exciting discovery that your flights really aren't doing much for you unless you have a poorly released dart. So maybe one thing you could do is get some old flights and butcher them and see does it matter for you? And if it does, what it might be telling you is that you're not releasing the dart straight, okay? I only use 2 fingers in my grip, and that's to minimize this kind of thing, to minimize any sort of little sideways force that my fingers are putting on the dart that might make it, the back kind of waggle around, okay? So I just use thumb and forefinger. My middle finger is just, it rests on the middle finger till the tiny moment of release, and then it's just 2 fingers. And that way, it's the least amount of error, I think, in the way the dart's released. So you might want to try that, okay? So what I'm going to do just to end this video then, this very different video to the one I thought I was going to make, is just have a quick game of 501 with these crazy darts. Try to give you a pretty good show with this. So if I don't do a good 501 on the first take, I'll do a couple of takes. But it's really just to convince you that you can totally mangle your flights and it doesn't actually seem to make that much difference to your game, as long as you really focus on throwing very smoothly and also delivering the dart in a very straight orientation along its trajectory. Okay, so here we go, 501. I might put the board light on just to help me see the board better. And we'll just see how we go on here. Okay, we're doing another take. Alright, that's 85 to start. What does that take us down to? Is that 416 after 1? And that's 45 there. So 416, 411, 371 after 2 visits. Another 85, 371, 366, 286 after 3. Wow, looks like a 180 there. It's not bad, is it? 286, what was that leave then? 186, 106 after 4, I think. 106 after 4. 86. Right. 50 left, I think, after 5. 50 left. Oh dear, that wasn't very good. All right, 16 left after 6. Come on, let's try and get this up in under 21 darts here. Okay, 20 darts. That's pretty good for me. That was not too bad at all. Let me turn the board light out then. And just to remind everyone, you know, that's those darts there. So I don't know, I don't find much difference with those darts. To be honest, I play better with these butchered darts, and the reason I play better is I know I have to throw smoothly. You know, I can't be kind of cavalier with the way I throw. So who knows? I mean, maybe this is the future of darts equipment, is just to kind of, I don't know, just because it doesn't seem to make any difference to where the darts land, to be honest. You know, I mean, some of my darts were kind of spraying around a bit there, but you know, I wasn't really aware of which flight I was throwing, you know, as I was playing. I was just in a different zone, really. So anyway, 3 darts at the Okier. The one thing that I haven't mentioned in this air resistance video is lift, okay, which is another force. I don't think lift is particularly relevant to these darts, okay. I think the form drag is a much bigger effect. But the lift will be there, and it will be part of the thing that essentially is pushing these darts into their, you know, following that parabolic arc, but it's not going to lead to any bigger force against the dart. So that's it, really. So the bottom line is then, the stuff we did in the 3rd and 4th videos is pretty much good enough for looking at the elite players, because they're going to be throwing very, very straight. So I can use those much simpler equations and so on to work out all of their statistics and I'm really looking forward to doing that series. And just a heads up here, I've got a video that I'm going to be producing soon, which I've been wanting to do it for ages, and it's all about something I call Darts 26, and I just can't wait to show you this. And it might be a really big deal on May the 2nd next year, so that's just a teaser there. So until then, everyone, I hope you're doing all right. 3 darts at the oche, make them count even if they've been butchered, and I'll see you next time.